Hello and welcome to Chapter 9 on our lectures, which is about the outer planets Jupiter, Saturn, Uranus, and Neptune. We begin with Jupiter, which is the largest of the planets, and also has one of these vital statistics pages that I'm just going to leave up for a few seconds before we start talking about everything that is on here. Jupiter is the largest planet in the solar system. More than 1,300 Earths could be packed into its volume. Using the orbital periods of its moons and Kepler's laws, astronomers have determined that Jupiter is 318 times more massive than Earth. Indeed, Jupiter has more than 2.5 times as much mass as all of the other planets combined. This huge mass has created the myth that Jupiter is a failed star, meaning that it has almost enough matter to shine on its own like the Sun, which we will study in Chapter 11. In fact, Jupiter would have to be 75 times more massive than it is to generate energy like the Sun, and therefore be classified as a star. Nevertheless, Jupiter emits approximately twice as much energy as it receives from the Sun. Its extra energy comes from radioactive elements in its core and from an overall contraction amounting to less than 10 centimeters per century. Contraction contributes to heating because when any matter is compressed, it heats up. Jupiter is permanently covered with clouds. Because it rotates about once every 10 hours, the fastest of any planets, Jupiter's clouds are in perpetual motion and are confined to narrow bands of latitude. Even though through a small telescope, you can see Jupiter's dark reddish bands called belts, alternating with light-colored bands called zones. The zones are white due to ammonia vapor at their tops, while the sources of the colors of the belts are still under investigation. These belts and zones are gases flowing eastward or westward with very little north-south motion. Such winds are called a zonal flow, and why some winds flow one way and some the other is still under investigation. In contrast, wind zones slower rotating Earth wander over vast ranges of latitude. Wind speeds between 310 kilometers per hour and 645 kilometers per hour are typical on Jupiter. Note that the belt and zone regions of Jupiter do not extend all the way to the planet's poles. Jupiter's belts and zones provide a framework for turbulence rolling cloud patterns, as well as rotating storms similar in structure to hurricanes or cyclones on Earth. These storms are known as white ovals or brown ovals. The white ovals are observed to be cool clouds higher than the average clouds on Jupiter's atmosphere. The brown ovals are warmer and lower clouds seen through holes in the normal cloud layer. The various oval features last from hours to centuries. Observations of radio emissions from Jupiter reveal that many of these storms extend down 100 kilometers below the visible surface of the planet. As you can see here, Jupiter's most striking feature is its Great Red Spot, which is so large that it can be seen through a small telescope. It was first observed around 1656 either by English scientist Robert Hooke or the Italian astronomer Giovanni Cassini. Because earlier telescopes were unlikely to have been able to see it, the Great Red Spot could well have formed long before that time. The feature changes dimensions dramatically. Sometimes it is very oval-shaped and 3 Earths could fit in it side by side, as was the case at the end of the 19th century. By 1980, it had shrunk so only 2 Earths could fit in it, and by 2018, it was only slightly larger than the diameter of Earth. The Great Red Spot is a hurricane-like or typhoon-like storm of swirling gases that extends at least 320 kilometers below the planet's surface. Heat welling upward from inside Jupiter has maintained it for more than 3.5 centuries. Between 1998 and 2000, 3 smaller white storms on Jupiter that formed in the 1930s merged, creating a larger white storm that became red in 2006, called Red Spot Junior. It is similar to and somewhat smaller than the Great Red Spot and located in nearly the same latitude. A third red storm joined the 2 red spots in 2008. As with the Great Red Spot, the cause of the red color in these 2 recent storms is still being studied. This coalescence of the white storms into Red Spot Junior can be seen in this diagram alongside the Great Red Spot itself. In 2017, astronomers observed a region at Jupiter's North Pole where the temperature is about 75 centigrade or 170 Fahrenheit colder than the surrounding gases. Now called the Great Cold Spot, it is similar in size to the Great Red Spot. Review of previous observations revealed that the Great Cold Spot has existed for at least 15 years, and possibly much longer. While the gases in this region may be cooled by interacting with the planet's magnetic field and the aurora, details are still being worked out. In 1690, Giovanni Cassini noted that the speeds of Jupiter's clouds vary with latitude, an effect called differential rotation. Near the poles, the rotation period of Jupiter's atmosphere, 9 hours, 55 minutes, and 30 seconds, is 5 minutes longer than at the equator. Furthermore, clouds at different latitudes circulate in opposite directions, some eastward, some westward. At their boundaries, the clouds rub against each other, creating beautiful swirling patterns. The interactions of clouds at different latitudes also helps provide stabilities for storms like the Great Red Spot. Jupiter's rapid rotation causes its equatorial radius to be 9,284 kilometers greater than its polar radius. All such rotating worlds, wider at the equator than at the poles, are said to be oblate, and the Earth is also an oblate spheroid. It is just not as pronounced as this. Astronomers first determined Jupiter's overall chemical composition from its average density, mass divided by volume. We determined Jupiter's mass using Kepler's third law and the orbital periods of its moons, while the trigonometry of Jupiter's distance from Earth and angular size in our sky reveals its diameter and hence its volume. This low density implies that Jupiter is primarily composed of the lightweight elements hydrogen and helium, surrounding a relatively small central volume thousands of kilometers below its cloud tops and containing water, metal, and rock. The planet has no solid continents, islands, or water oceans on its surface. Because of the primary elements are hydrogen and helium, Jupiter and Saturn are called gas giants. Spectra from Earth-based telescopes and from the Galileo probe sent into Jupiter's upper atmosphere in 1995 give more detail about the chemistry of this giant world's upper level. About 86% of its atoms are hydrogen and 13% are helium. The remainder consists of molecular compounds such as methane, ammonia, and water vapor. Keeping in mind that different elements have different masses, we can convert their percentages of atoms into the masses of various substances in Jupiter's atmosphere: 75% hydrogen, 24% helium, and 1% other substances. Because the interior contains heavier elements than the surface, the overall mass distribution in Jupiter has been calculated to be 71% hydrogen, 24% helium, and 5% heavier elements. Observations from spacecraft visiting Jupiter and its moons, combined with the scientific model of Jupiter's atmosphere, developed to explain the observation of Jupiter's clouds and chemistry, indicated that it has three major clouds layers. The uppermost Jovian cloud layer is composed of crystals of frozen ammonia. These crystals and frozen water in Jupiter's clouds are white, so what chemicals create the subtle tones of brown, red, and orange? As noted earlier, the answer is as yet unknown. Some scientists think that sulfur compounds, which can assume many different colors depending on their temperature, play an important role. Others think that phosphorus is involved, especially in the Great Red Spot. The middle cloud layer is primarily ammonium hydrosulfide, and the bottom cloud layer is mostly composed of water vapor. Looking at these layers between Jupiter and Saturn, we see that Jupiter has much more compressed layers, while Saturn, which has a lower gravitational pull, is not able to compress the layers as much. But overall, they are very similar to each other. Below its cloud layer, Jupiter's mantle is entirely liquid. Here on Earth, the distinction between the gaseous air and the liquid oceans is very clear. Jump off a diving board and you know when you hit the water. However, the conditions on Jupiter under which hydrogen liquefies are different from anything we normally experience. Solid, liquid, and gas are called phases of matter. Transforming from one phase of matter in everyday life is called a phase transition. Under conditions of extreme pressure and temperature, phase transitions do not occur. As a result, on Jupiter there is no definite boundary between the planet's gaseous atmosphere and its liquid mantle. The hydrogen gradually gets denser until 1,000 kilometers below the cloud tops. The pressure is high enough for the hydrogen to be what we would consider a liquid. In introducing the solar system, we noted that the young planets heated up as they coalesced. After they formed, radioactive elements continued to heat their interiors. On Earth, this heat leaks out of the surface through volcanoes and other events. Jupiter loses heat through its clouds everywhere because, unlike Earth, it has no surface land masses to block the heat loss. Still heated from deep within Jupiter, blobs of liquid hydrogen and helium move upward inside the planet. When these blobs reach the cloud tops, they release their heat and descend back into the interior. The same process, convection, drives the motion of Earth's mantle and its tectonic plates, as well as liquid simmering on a stove. Jupiter's rapid differential rotation draws the convective gases into bands of winds moving eastward and westward at different speeds around the planet. Astronomers believe that Jupiter's belts and zones result from the combined actions of the planet's convection and rapid differential rotation. The light-colored zones are regions of hotter rising gas, while the dark belts are regions of cooler coalescing descending gas. Measurements by the Juno spacecraft reveals that the belt and zone structure extends 3,000 kilometers into Jupiter. Descending below Jupiter's clouds, we first encountered liquid molecular hydrogen and helium. As in Earth's ocean, the pressure of this fluid increases with depth. The gravitational forces created by Jupiter's enormous mass compresses and heats its interior so much that 20,000 kilometers below the cloud tops, this pressure is 3 million atmospheres. Below this depth, the pressure is high enough to transform hydrogen into liquid metal hydrogen. In this state, hydrogen acts like a metal in its ability to conduct electricity and heat. Electric currents that run through this rotating metallic region of Jupiter generate a powerful planetary magnetic field, 10 times stronger than the strongest magnetic field measured on Earth. Beginning with the 2 Pioneer and 2 Voyager spacecraft that journeyed past Jupiter in the 1970s and continuing with the recent Galileo and Cassini spacecraft, the awesome dimensions of Jupiter's magnetosphere have been revealed. It is nearly 30 million kilometers across and envelops the orbit of many of its moons. If Jupiter's magnetosphere were visible from Earth, it would cover an area of the sky 16 times larger than the moon as seen from here. At the cloud level of Jupiter, this field is 14 times stronger per square meter than Earth's field is at our planet's surface. Jupiter's magnetic field has a region, like Earth's Van Allen belts, where charged particles are stored, and its tail, called the magnetotail, streams outwards as far as Saturn, over 700 million kilometers away. This magnetosphere and magnetotails and aurora can all be seen in this diagram, which give an idea of how strong Jupiter's magnetic field is. Recall from Chapter 6 that impacts were extremely common in the first 800 million years of the solar system's existence. From more recent times, 2 chains of impact craters have been discovered on Earth, consistent with pieces of comets having hit our planet within the last 300 million years. However, it is very uncommon for pieces of space debris as large as several kilometers in diameter to collide with planets today. Therefore, the discovery that Shoemaker-Levy 9 would hit Jupiter created great excitement in the astronomical community. Seeing how the planet and a comet responded to such impact would allow astronomers to deduce information about the planet's atmosphere and interior, as well as about the striking body's properties. The impacts occurred as predicted, with most of Earth's major telescopes, as well as those of several spacecraft, watching closely. At least 20 fragments from Shoemaker-Levy 9 struck Jupiter, and 15 of them had detectable impact sites. The impact resulted in fireballs some 10 kilometers in diameter with temperatures of 7,500 Kelvin, which is hotter than the surface of the Sun. Indeed, the largest comet fragment gave off as much energy as 600 million megatons of TNT, far more than the combined energy that could be released from all the nuclear weapons currently stockpiled on Earth. Impacts were followed by crescent-shaped ejecta that contained a variety of chemical compounds. Ripples or waves spread out from the impact sites through Jupiter's clouds in splotches that lasted for months. The observations suggested that the pieces of comet did not penetrate very far into Jupiter's upper cloud layer. The fact, in turn, supports the belief that the pieces were not much larger than a kilometer in diameter. The ejecta from each impact includes a dark plume that rose higher into Jupiter's atmosphere. The darkness was apparently due to carbon compounds that vaporized from the cometary bounds. Bodies also detected from the comet collision were water, sulfur compounds, silicon, magnesium, and iron. Jupiter hosts at least 79 moons, The four largest, Io, Europa, Ganymede, and Callisto, may have formed at the same time as Jupiter from debris orbiting the planet, just as the planets formed from debris orbiting the Sun. Jupiter's other moons are probably captured planetesimals and smaller pieces of space debris. Galileo was the first person to observe the four largest moons. In 1610, seen through his meager telescope as pinpoints of lights, he called them the Medicean stars to attract the attention of the Medicis, rulers of Florence and wealthy patrons of the arts and science. To Galileo, the moons provided evidence supporting the then controversial Copernican cosmology. At that time, Western theologians asserted that all cosmic bodies orbited Earth. The fact that the Medicean stars orbited Jupiter raises grave concerns in some circles. I will also state that they are now called Galilean moons rather than Medicean stars, as that is going to be the term that we're using further in the lecture. Sulphurus Io is among the most exotic moons in our solar system. At first glance, this moon's density seems to place its chemical composition between that of the terrestrial and Jovian planets. However, its density has value in large measure because its mass is so small that it cannot compress its interior nearly as much as Earth can, or more massive planets can. Allowing for its lower composition, astronomers calculate that Io is mostly rock and iron, like Earth, rather than being composed of lighter elements, as is Jupiter. Io zooms through its orbit of Jupiter about once every 1.8 days. Like our moon, it is in synchronous rotation with its planet. Images of Io reveal giant plumes emitted by about 400 active volcanoes and lava geysers. Most of this ejected material falls back onto Io's surface. The rest is moving fast enough to escape into space. Besides the violent ejections of lava, Io also has volcanoes out of which lava just pours rather than spurts. Observations indicate that Io's volcanoes emit 10 trillion tons of lava each year in plumes up to 400 kilometers high. This is 100 times as much lava as is emitted by all Earth's volcanoes. That amount of material is enough to resurface Io to a depth of 1 meter each century. One eruption in 2002 occurred over an area the size of London, some 1,600 square kilometers. In 2014, astronomers observed a volcanic eruption that ranks as the most powerful such event ever recorded, emitting 2 times 10 to the 13 watts of energy. Light bulbs generally emit less than 100 watts. The volcanoes emit basaltic lava flows rich in magnesium and iron. Io's volcanoes are named after gods and goddesses associated with fire in Greek, Norse, Hawaiian, and other mythologies. Io also has mysterious black dots on its surface, which apparently are dormant volcano vents. Old lava flows radiate from many of these locations, which are typically 10 to 50 kilometers in diameter and cover 5% of Io's surface. Images of Europa's ice and rock surfaces from Voyager 2 and the Galileo spacecraft reveal that the interior of Jupiter's second closest Galilean moon contains liquid water. Europa orbits Jupiter every 3.5 days, and like Io, is in synchronous rotation. The changing gravitational tug of Io creates stress inside Europa similar to the magma-generating distortion that Io undergoes. These stresses apparently cause the numerous cracks or fractures seen on Europa's surfaces. In 2014, astronomers reviewing images from Galileo identified the signature of tectonic plate motion on Europa, where one plate glides under another. Furthermore, astronomers think that the stress caused by the surface motion helps heat inside Europa, thereby keeping water in a liquid state just a few kilometers below the moon's ice and rock surface. To prevent the expired spacecraft Galileo from contaminating any life that may exist, as there is liquid water on Europa, NASA sent that spacecraft into Jupiter's thick atmosphere where the machine was vaporized. Ganymede is the largest satellite in the solar system. Its diameter is greater than Mercury's, but its density is much less than that of Mercury. The moon also has a permanent magnetic field that's twice as strong as Mercury's field. Ganymede orbits Jupiter in synchronous rotation at once every 7.2 days. Like its neighbor Europa, Ganymede has an iron-rich core, a rocky mantle, an icy mantle, a salty underground liquid water ocean, a covering of dirty ice, and a thin atmosphere. The existence of an underground ocean is implied by the discovery of a second magnetic field around Ganymede, which continually varies. The field has a different origin than any of the permanent one just mentioned. The second field is generated by Jupiter's magnetic field. As Ganymede orbits Jupiter, the planet's powerful magnetic field creates an electric current inside the moon, which in turn creates Ganymede's varying magnetic field. The field varies as the moon rotates and as it revolves around Jupiter. The best explanation of why current flows inside Ganymede is that the liquid salt water exists there, and salt water is a good conductor of electricity. This implies, of course, the presence of a liquid ocean. Furthermore, salts have been observed on Ganymede's surface. They were apparently carried upward and deposited there as water leaked out and froze. As on Europa, liquid water may imply the presence of life. Callisto is Jupiter's outermost Galilean moon. It orbits Jupiter in 16.7 days, and like the other Galilean moons, its rotation is synchronous. Callisto is 91% as big and 96% as dense as Ganymede, and has a thin atmosphere of hydrogen and carbon dioxide. Like Ganymede, Callisto apparently harbors a substantial liquid water ocean. As with Ganymede, this ocean's presence is inferred by Callisto's changing magnetic field. The heat that keeps the ocean liquid likely comes from energy released by radioactive decay inside the moon. Although numerous large impact craters are scattered over Callisto's dark, ancient icy crust, it has very few craters smaller than 100 meters across. Astronomers speculate that the small craters have disintegrated. Unlike Ganymede and Europa, Callisto has no younger groove terrain. The absence of groove terrain suggests that tectonic activity never began there, probably because the satellite simply froze too rapidly. It is barely cold on Callisto's surface. Voyager instruments measured a noontime temperature of 155 Kelvin, or negative 180 degrees Fahrenheit, and a nighttime temperature of 80 Kelvin, or negative 315 degrees Fahrenheit. Along with the 4 Galilean moons, Jupiter has at least 65 other moons, a set of tenuous ringlets, and 2 donut-shaped tori of electrically charged gas particles. The non-Galilean moons are all irregular in shape and less than 275 kilometers in diameter. 4 of these moons are inside Io's orbit. All of the other known moons are outside Callisto's orbit. The inner moon, Amalthea, is red-colored, has about the same density as water, and is apparently made of pieces of rock and ice barely held together by the moon's own gravity. The Galilean moons, along with the smaller moons closer to Jupiter and 6 of the outer moons, orbit in the same revolution that Jupiter rotates, prograde orbits. The remaining outer moons revolve in the opposite direction, retrograde orbits. The outer ones appear to be individually captured planetesimals, while the inner ones are probably small pieces of broken off of a single larger body. Along with the 4 Galilean moons, Jupiter has at least 65 other moons, a set of tenuous ringlets, and 2 donut-shaped tori of electrically charged gas particles. The non-Galilean moons are all irregular in shape and less than 275 kilometers in diameter. 4 of these moons are inside Io's orbit. All of the other known moons are outside of Callisto's orbit. The Amalthea is red-colored, has about the same density as water, and is apparently made of pieces of rock and ice barely held together by the moon's own gravity. The Galilean moons, along with some smaller moons closer to Jupiter and 6 of the outer moons, orbit in the same direction as Jupiter rotates, prograde orbits. The remaining outer moons revolve in the opposite direction, retrograde orbits. The outer ones appear to be individually captured planetesimals, while the inner ones are probably smaller pieces broken off of a single larger body. Jupiter is only the first of 4 planets with rings. Its ring system is composed of several parts. Debris knocked off from the moons Adrastea and Metis is responsible for the main ring. The outer edge of the ring has well-defined ringlets that are pieces of debris ranging in size from gravel to small boulders. The rest of the ring, extending about 10,000 kilometers inward towards Jupiter, is composed of dust-sized particles. This ring is less than 50 kilometers thick. Apparently, some of the smallest particles leak inward, creating the halo ring. Debris ejected from the moons Amalthea and Thebe create thicker rings of very tiny dust particles called gossamer rings, while some of the ring materials continually being ejected by collisions between particles and by radiation from the sun. Impacts freeing regolith from the moons are continually replenishing all the rings. At least 2 donut-shaped regions, or tori, of electrically charged gas particles cause called plasmas orbit Jupiter as is seen. Moving on, we get to Saturn. Saturn, with its ethereal rings, presents the most spectacular image of the planets. Giant Saturn has 95 times as much mass as Earth, making it second in mass and size to Jupiter. Like Jupiter, Saturn has a thick, active atmosphere composed predominantly of hydrogen. Indeed, the percentage of hydrogen is higher in Saturn's atmosphere than in Jupiter's atmosphere. Saturn also has a strong magnetic field. Ultraviolet images from the Hubble Space Telescope reveal aurorae around Saturn differing from those of Jupiter in that Saturn's aurorae are spirals while Jupiter's are rings. Here again are the vital statistics of Saturn. Partly obscured by the thick hazy atmosphere above them, Saturn's clouds lack the colorful contrast visible on Jupiter. Nevertheless, photographs do show faint stripes on Saturn's atmosphere, similar to Jupiter's belts and zones. Their existence indicates that Saturn also has internal heat transports that the cloud gases by convection. Changing features on the atmosphere show that Saturn II has differential rotation, ranging from about 10 hours and 14 minutes at the equator to 10 hours and 40 minutes at high latitudes. As on Jupiter, some of the belts and zones move eastward while others move westward. Unlike Jupiter, however, Saturn's belts and zones extend all the way from the equator to As noted before, the chemical composition of the planet's atmosphere is different from that of Jupiter. Saturn's atmosphere is about 96.3% hydrogen and 3.3% helium, while Jupiter has about 89.8% hydrogen and 10.2% helium. A related observation is that Saturn emits about 2.3 times as much energy as it receives from the Sun. Unlike Jupiter, whose extra energy is emitted primarily by Kelvin-Helmholtz mechanism, much of Saturn's extra energy is believed to be generated by a mechanism called helium rain. Helium rain works like this. Because it is smaller than Jupiter and farther from the Sun, Saturn's atmosphere is cool enough for the helium in it to condense into liquid droplets. The helium rain that then descend deep into the planet. As it strikes the interior, the rain's energy helps heat the planet, which in turn radiates that energy. Saturn's rotation axis is tilted by 26.7 degrees compared to the plane of its orbit around the Sun. Just as Earth's orbital inclination causes seasons here, it was suspected that Saturn's might have seasons too. This was confirmed by observations and measurements taken by the Cassini spacecraft over a period of Saturn's orbit around the Sun, one Saturnian year. Saturn's upper atmosphere is about 10 centigrade warmer in summer than in winter. The color of each hemisphere changes from yellow-orange in summer to bluish hues in winter. The changing color is the result of changing combinations and dissociations of atoms, creating different molecules that scatter different colors of sunlight in different seasons. Because of its smaller mass, Saturn's interior is also less compressed than Jupiter's, so the pressure inside Saturn is insufficient to convert as much hydrogen into liquid metal. Saturn's rocky core is about 7,400 kilometers in radius, while its layer of liquid metal hydrogen is 12,000 kilometers thick. To alchemists, Saturn was associated with the extremely dense element lead. This is wonderfully ironic in that at 687 kilograms per meters cubed, Saturn is on average the least dense body in the entire solar system. An object with that density on Earth would float on water. It is also interesting that because of the orientation of the rings and the declination of the planet, sometimes when you look at Earth, or when you look at Saturn from Earth, you can barely see the rings, while at other times when you look at Saturn from Earth, they are quite visible. Saturn's rings are tilted 27 degrees from the perpendicular to the Saturn's plane of orbit, so sometimes they are nearly edge onto us, making them impossible to see from Earth. In 1675, Giovanni Cassini discovered an intriguing feature, a dark division in rings. This 5,000-kilometer gap, called the Cassini division, separates the dimmer A ring from the brighter B ring, which lies closer to the planet. By the mid-1800s, astronomers using improved telescopes detected a faint C ring just inside the B ring, where there are actually quite a few rings up here, all the way from A to F, as we have discovered more and more rings and more boundaries between them. The Cassini division occurs because the gravitational force from Saturn's moon Mimas combines with the gravitational force from the planet to keep this region relatively clear of debris. Whenever matter drifts into the Cassini division, Mimas, orbiting at a different rate than the matter in the Cassini division, periodically exerts a force on this matter, eventually pulling most of it out of the division. This effect is called resonance and is similar to what happens when you repeatedly push someone on a swing at the right time, giving them energy that enables them to go higher and higher. Despite its resonance keeping the Cassini division relatively clear of larger debris, it is filled with dust-sized particles. We know this because, like particles near a window in a room with sunlight streaming in, such dust-sized particles in the Cassini division scatter light forward rather than backwards as larger pieces of matter do. We see everything around us because these things scatter light back off their surface towards us. Dust primarily scatters forward, while the Cassini spacecraft passes Saturn and looks back at its dark side. The dust particles in the Cassini division and also the Encke division scattered light forward toward the spacecraft so that these divisions were not as dark when seen from that perspective. A second gap called the Encke division exists in the outer portion of the A-ring. Unlike the Cassini division, the Encke division is kept clear because of a small moon Pan orbits within it. Encke's division is named after the German astronomer Johann Franz Encke, who allegedly saw it in 1838. The first undisputed observation of the 270-kilometer wide division was made by the American astronomer James Killer in the late 1800s with the newly constructed 36-inch refractor at the Lick Observatory in California. A 40-kilometer space near the outer ring of the bright A-ring is now named after the Killer Gap in honor of his work. The gravitational tugs of Pan, Daphnis, Prometheus, and other moons all cause the rings to ripple. The Voyager cameras sent back the first high-quality pictures of the F-ring, a thin set of ringlets just beyond the outer edge of the A-ring. Two tiny satellites, Prometheus and Pandora, have orbits on either side of the F-ring and serve to keep it intact. The outer of the two satellites orbits Saturn's at a slower speed than do the ice particles in the ring, as governed by Kepler's third law. As the ring particles pass near it, they receive a tiny backwards gravitational pull, which slows them down, causing them to fall fast into orbits a little bit closer to Saturn. Meanwhile, the inner satellite orbits the planets faster than the F-ring particles. The moon's gravitational orbit pulls them forward and nudges the particles back into a higher orbit. The combined effect of these two satellites causes the icy particles to a well-defined narrow band of about 100 kilometers wide. In 2010, the Cassini spacecraft observed these snowballs as large as 20 kilometers in diameter forming in the F-ring. These bodies form as small bits of the F-ring debris swirl around and collide with each other under the gravitational attractive force of the passing moon Prometheus, which tugs on them. At other times, large pieces collide and break into smaller ones. Because of their confining influence, Prometheus and Pandora are called shepherd satellites or shepherd moons. Among the most curious features of the F-ring is that the ringlets sometimes braid or intertwine and sometimes separate. Although stabilized by the shepherd moons, the F-ring does ripple and shows varying brightness. Astronomers theorize that the changes in brightness result from collisions between clumps of matter in the ring. A promising theory has been put forth to explain the origin of ice-rich rings on Saturn, we have just been discussing. Just as the planets formed in a disk around the protosuns, astronomers believe that Saturn's largest moons include Rhea, Titan, and Iapetus, formed a disk of gas and dust orbiting the younger Saturn. Another moon is posited to have formed at the same time in an orbit closer to Saturn than these moons. Recall from the NEAS model that Saturn formed during a period in when there were myriad pieces of debris in its orbit and crossing its orbit. That debris took energy away from Saturn, which was why it initially spiraled sunward. This theory proposes that the innermost moon, buffeted by the same debris, lost energy and spiraled inward towards Saturn. Eventually, it crossed the Roche limit, or the Roche limit, the distance at which a planet creates tides on a moon's solid surface high enough to pull its moon apart. The tidal force stressed the moon, causing much of the ice-rich surface to be stripped off and inserted into orbit as the denser rocky debris continued spiraling inwards until it sank into the planet. The remaining icy debris became the major rings of Saturn. The particles that form Saturn's rings must be highly reflective because the rings are very bright, with an albedo of 0.8. The astronomers had long suspected that the Earth's The ring consists primarily of water ice along with ice-coated rocks. Spectra taken by Earth-based observatories by the spacecraft visiting Saturn have confirmed that suspicion. While the temperature of the rings ranges from 93 Kelvin, or negative 90 degrees Fahrenheit, in the sunshine to less than 73 Kelvin, or negative 330 degrees Fahrenheit, in Saturn's shadow, water particles are nevertheless being freed from them, probably by ultraviolet radiation from the sun. The water particles are guided toward Saturn by the planet's magnetic field, where they combine with other particles in Saturn's upper atmosphere. Saturn's rings are slightly salmon-colored. This coloring suggests that they contain traces of organic molecules which often have such hues. It appears that the rings have gained this material by being bombarded with debris from the outer solar system. As in Jupiter, Saturn's internal layer of liquid metallic hydrogen produces a plant-wide magnetic field that affects its rings. To Saturn's much smaller volume of liquid metallic hydrogen, the magnetic field at Saturn's surface is only about two-thirds as strong as the magnetic field on Earth. Data from spacecraft show that Saturn's magnetosphere contains radiation belts similar to Earth's Van Allen belts. Furthermore, dark spokes around Saturn's ring. These are believed to be created by electric charges on the rings, materials interacting with the planet's magnetic field. The magnetic field lifts charged particles out of the plane on which the rings orbit. Spreading the particles out decreases the light scattered from them and therefore makes spoke-like features in the rings appear darker. The magnetic field, moving with the planet as it rotates, causes the regions of spread to change, making the spokes appear to revolve around the planet. Saturn's largest moon, Titan, is second in size to Ganymede among the moons of the solar system and is the only moon in the solar system found in its atmosphere. Like many other moons of Saturn, Titan is in synchronous rotation the planet. About 10 times more gas lies above each square meter of Titan's surface than lies above each square meter of Earth. As a result, the air pressure on the surface of Titan is about 1.5 times the air pressure we feel on Earth. Christian Huygens discovered Titan in 1655, the same year he proposed that Saturn has rings. By the early 1900s, several scientists had begun to suspect that Titan might have an atmosphere. The moon is larger, although less massive than Mercury, and far colder than the planet. Calculations reveal that Titan is cool enough and massive enough to retain heavy gases in the atmosphere. Because of this, Titan was the primary target for the Voyager missions. Unexpectedly, its thick haze blocked any primary target or any view of its surface. Observations also reveal clouds of methane form and dissipate seasonally near both of Titan's poles and in the mid-southern latitudes. Although the causes for the appearance and disappearance of these clouds is not known, Titan has been observed to have lakes of ethane, methane, and propane. Geysers and evaporation from Titan's lakes are considered as possible factors in creating these clouds. Spacecraft have detected small amounts of nearly 20 hydrocarbons in Titan's atmosphere, including ethane, acetane, ethylene, and propane. Methane and ethane condense into droplets in the cold air, making Titan the only other world in the solar system besides Earth where rain reaches the surface. The rain, however, is very different from on the two worlds. Titan's raindrops are calculated to be about 1 centimeter in diameter, about twice as large as the large raindrops on Earth, and because of Titan's low surface gravity, they fall 6 times slower than raindrops here. Rain on Titan falls at the speed of slowly falling snowflakes on Earth. Nitrogen combines with various hydrocarbons to produce other compounds that can exist as liquid on Titan. Although one of these compounds, hydrogen cyanide, is a poison, some of the others are the building blocks of life's organic molecules. Indeed, biologists who study Titan's atmosphere now think that its chemistry is very similar to that of a young Earth. Many of the hydrocarbons and carbon and nitrogen compounds in Titan's atmosphere can form complex compounds called polymers. These molecules are long-repeating chains of atoms. Rubber, cellulose, and plastics are the best-known examples on Earth. Scientists hypothesize that droplets of lighter polymers remain suspended in Titan's atmosphere and form a mist, while heavier particles settle down into Titan's surface. Images of this surface taken by the Cassini spacecraft, which arrived in the Titan system in 2004, show few craters, indicating that Titan's surface undergoes dynamic changes. Despite this fact, that activity is in its atmosphere and surface continually covers craters and other surface features, Titan does not have a mountain range with peaks, or Titan does have a mountain range with peaks as high as 1.5 kilometers. These peaks are covered with organic matter and possible methane snow. We have little reason to suspect that life exists on Titan's surface because the temperature there, 95 Kelvin or negative 288 degrees Fahrenheit, is prohibitively cold. However, in 2008, astronomers using data from Cassini discovered that surface features, including lakes, canyons, even mountains, drift some 15 kilometers per year. They conclude that this drift is because the salty liquid water ocean exists 100 kilometers under Titan's surface. That layer acts as a lubricant that allows the surface to move relative to the deep interior, which has been determined to be a mix of rock and ice. The combination of liquid water and organic compounds such as methane may enable life to have evolved inside of Titan. Rheus, Saturn's second largest moon, is in synchronous rotation. Astronomers have observed that its leading face has many more craters than its trailing face. This moon has a density consistent with it being composed mostly of water ice with rocky debris mixed in. In 2008, Cassini spacecraft observed white and blue ice features on its trailing side that are associated with scarps, long lines of cliffs, like those found on Mercury. In 2010, Cassini detected an atmosphere containing 70% oxygen and 30% carbon dioxide. It is about 100 times thicker than the atmosphere on Mercury. Saturn's sixth largest moon, Enceladus, moved from the sidelines towards center stage in 2005 as Cassini began studying it. Discovered in 1789 by William Herschel, this bright world has an icy, wrinkled surface similar in appearance to Jupiter's Europa and Ganymede. The fact that these latter two bodies contain liquid water was the first clue that Enceladus does too. This theory is supported by other observations that the entire regions of Enceladus' southern hemisphere are free of craters. Indeed, there are ice blocks the size of large houses which have been apparently erased many craters due to tectonic plate motion. In addition, the spacecraft revealed that dark lines on Enceladus, dubbed tiger strikes, are no more than a few million years old. These features, much warmer than the surrounding surface and heated from below, are cracks through which water wells up from inside, freezing into a smooth, dark surface. The tiger stripes are typically 100 kilometers long and 35 kilometers apart. The next planet, Uranus, is so far away that it is virtually invisible to the naked eye, and was the first planetary system discovered by a telescopic search of the heavens. The planet is 19.2 astronomical units away from the Sun and takes 84 years to orbit, or Earth years to orbit. Since its discovery in 1781, Uranus has orbited the Sun fewer than 3 times. Until early 1996, observations of Uranus, the fourth most massive planet in our solar system, revealed few notable features in the visible part of the spectrum. Even the 1986 visit of Voyager 2 showed a remarkably bland world. It took the Hubble Space Telescope's infrared camera to find what Voyager's visible light camera could not. Uranus had a system of belts and zones. Its hydrogen and atmosphere has traces of methane along with high-altitude haze, under which are clear air and ever-changing methane clouds that dwarf the typical cumulus clouds we see on Earth. Uranus's clouds are towering and huge, each typically as large as Europe. Along with the rest of the atmosphere, the clouds go around the planet once every 16 and a half hours, which variation due to differential rotation as also occurs on Jupiter and Saturn. Uranus contains 14.5 times as much mass as Earth and is 4 times bigger in diameter. Its outer layers are composed predominantly of gaseous hydrogen and helium. The temperature in the upper atmosphere of the planet is so low that the methane and water there condenses to form clouds of ice crystals. Because methane freezes at a lower temperature than water, methane forms higher clouds over Uranus than it does water vapor. Methane efficiently absorbs red light while scattering blue and green, thereby giving the planet its blue-green color. At the very top of Uranus's clouds is a layer of hydrogen sulfide gas. On Earth, that gas smells like rotten eggs. Here again are the vital statistics for Uranus. Because Uranus's axial tilt is almost perpendicular to the plane of the ecliptic, it is always going to have seasons in the same way that we have seasons caused by our 23-degree axial tilt, since Uranus is basically always pointing directly, has a pole always pointing directly towards or away from the Sun. It is going to have more aggressive seasons or more pronounced seasons than we will see here on Earth. Because its north pole points below the plane of its orbit around the Sun, Uranus is one of only two planets with retrograde rotation, Venus being the other. As Uranus orbits the Sun, its north and south poles alternately point almost directly towards or directly away from the Sun, producing exaggerated seasons. In the summertime, near Uranus's north pole, the Sun is almost directly overhead for many Earth years, at which time southern latitudes are subjected to a continuous frigid winter night. 42 Earth years later, the situation is reversed. From its mass and density, astronomers conclude that Uranus's interior has three layers. The outer 30% of the planet is liquid hydrogen and helium. The next 40% inward is highly compressed liquid water, with some methane and ammonia, and the inner 30% is a rocky core. Ammonia dissolves easily in water, so a large ocean would explain the scarcity of the gas in the planet's atmosphere. As with Jupiter and Saturn, Uranus and Neptune have no phase transition between what we would call their atmospheres and the liquid layers directly below. In other words, they have no well-defined liquid surface. Because Uranus and Neptune are so rich in water, they are called ice giants. Uranus's surface magnetic field is about 3/4 that of Earth. That strength is reasonable considering the planet's mass and rotation rate, but everything else about the magnetic field is extraordinary. The field is remarkably tilted 59 degrees from its axis of rotation, and its axis does not even pass through the center of the planet. The magnetosphere of Uranus wobbles considerably as the planet rotates because of the large angle between the magnetic field of Uranus and its rotational axis. A rapidly changing magnetic field like this occurs elsewhere in astronomy. For example, it helps to explain the behavior of pulsars, a type of stellar remnant we will study in Chapter 14. Astronomers use Uranus's magnetic sphere's wobble to determine that the planet's interior rotates once every 17 hours 14 minutes. This is considerably slower than the 16.5-hour rotation of the clouds on its surface. Here we see the magnetic fields of some of the planets, and unlike Earth, Uranus and Neptune do not have magnetic fields going through their center, but are rather off-axis and off from the center of the planet. Uranus has 13 known rings, each divided into ringlets. The first 9 of the thin, dark rings were discovered accidentally in 1977 when Uranus passed in front of a star. The star's light was momentarily blocked by each ring, thereby revealing their existence to astronomers. Blocking of the light of a more distant object, such as the star here, by something between it and us, such as Uranus's rings, is called occultation. The other rings were detected by Voyager and the Hubble Space Telescope. The rings are held in orbit by shepherd moons, including Cordelia and Ophelia. This discovery of the rings is shown in this diagram, where as Earth passes by Uranus, the star on the left of the diagram is going to be blocked off by the separate rings as they block out some of the sunlight that is coming from this star. Comparing observations taken 30 years apart between the 1970s and the first decade of the 21st century reveals that the moons in the vicinity of the rings are changing orbits due to the mutual gravitational influences and the gravitational tugs of the rings. Furthermore, some of the ring debris is being lost and replaced by debris blasted off the moons as a result of meteorite impacts. Observations suggest that the moon MAB, discovered in 2003, is supplying the dust for the outermost ring. Miranda is the most fascinating and bizarre of Uranus's moons. Unusually wrinkled and banded features cover Miranda's surface. Its highly varied terrain suggests that it was once seriously disturbed. Perhaps shattering impact temporarily broke it into several pieces that then recoalesced, or perhaps severe tidal heating, as we saw on Io, moved large pieces onto its surface. Neptune, the outermost planet in the solar system, is physically similar to Uranus. Neptune has 17.1 times Earth's mass, 3.88 times Earth's diameter, and a density of 1640 kilograms per meters cubed. Its rapid rotation draws its clouds into belts and so on. Unlike on Uranus, however, cloud features can readily be discerned on Neptune. Its whitish citrus-like clouds consist of methane ice crystals. As on Uranus, the methane absorbs red light, leaving the planet's belts and zones with a banded bluish appearance. Like the other giant planets, the atmosphere of Neptune experiences differential rotation. The winds on Neptune blow at speeds of up to 2,000 kilometers per hour, among the fastest known in the solar system. Neptune's rotation axis is tilted nearly 30 degrees from the plane of its orbit around the Sun, and Hubble's Space Telescope observations of Neptune in 2003 showed seasonal changes near its poles. Here are the vital statistics for Neptune. And here's an infrared picture of Neptune. Neptune's discovery is storied because it illustrates a scientific prediction leading to an unexpected discovery rather than an unexpected discovery. Recall from section 210 that in 1781 the British astronomer William Herschel discovered Uranus. The planet's position was carefully plotted, and by the 1840s it was clear that, even considering the gravitational effects of all the known bodies in the solar system, Uranus was not following the path directly predicted by Newton's and Kepler's laws. Either the theories behind these laws were wrong, or there had to be another yet-to-be-discovered body in the solar system pulling on Uranus. Independent, nearly simultaneous calculations by an English mathematician, John Couch Adams, and a French astronomer, Urbain Le Verrier, predicted the same location for the alleged planet. That planet, Neptune, was located in 1846 by the German astronomer Johann Galle, within a degree or two of where it had to have been to have the observed influence on Uranus. Neptune's interior is believed to be very similar in composition and structure to that of Uranus, a rocky core surrounded by ammonia and methane-laden water. Neptune's surface magnetic field is about 40% of that of Earth. As with Uranus, Neptune's magnetic axis, the line connecting its north and south magnetic poles, is tilted sharply from its rotational axis. In this case, the tilt is 47 degrees. Also, like Uranus, Neptune's magnetic axis does not pass through the center of the planet. We saw in section 9.2 that the magnetic fields of Jupiter and Saturn are believed to be generated by the motion of their liquid metallic hydrogen. However, Uranus and Neptune lack this material, and their magnetic fields have a different origin. These fields are believed to exist because molecules such as ammonia, which dissolve in their water layers, lose electrons, become ionized. These ions, moving with the planet's rotating fluid interiors, create the same dynamo effect and hence the magnetic field. Like Uranus, Neptune is surrounded by a system of thin, dark rings. At these distances from the Sun, it is so cold that both planets' rings particles retain methane ice. Scientists speculate that eons of radiation damage have converted this methane ice into darkish carbon compounds, thus accounting for the low reflectivity of the rings. Neptune has 14 known moons. 13 have irregular shapes and highly elliptical orbits, which suggests that Neptune captured them. Triton, discovered in 1846, is spherical and was quickly observed to have a nearly circular retrograde orbit around Neptune. It is difficult to imagine how a planet rotating one way and a satellite revolving the other way would form together. Indeed, only the small outer satellites of Jupiter and Saturn have retrograde orbits, and these bodies are probably captured asteroids. Some scientists have therefore suggested that Triton was also captured 3 or 4 billion years ago by Neptune's gravity. Upon being captured, Triton was most likely a highly elliptical orbit. However, the tides that the moon creates on Neptune's liquid surface would in turn have made Triton's orbit more circular. Triton's average density of about 2,100 kilograms per meters cubed indicates that it is an equal mix of rock and ice. It has a thin nitrogen, methane, and carbon dioxide atmosphere, which changes density with the seasons on that world. When Triton was younger, the tidal forces exerted on it by Neptune due to the moon's initially elliptical orbit caused Triton to stretch and flex, providing enough energy to melt much of its interior and obliterate its original surface features, including craters. Note that very few craters are visible. While cratering continued, so did resurfacing. Calculations indicate that Triton's present surface is only about 100 million years old.